problems really have 4 steps that you want to follow when you do them. The first one is pretty much really the most important, which is you want to make sure you have a balanced equation. Remember that nothing works correct in terms of stoichiometry if you do not have that balanced equation. So pretty much stoichiometry is based off of that. You always want to make sure, even if the equation is given to you, that you do take a look at it, make sure it's balanced. Next thing that you want to do is take whatever they give you and pretty much convert to moles. So as we talked about, in a lot of cases, that's going to be sort of a grams to mole conversion. And that's a very common stoichiometry conversion. And we use, again, the molar mass to do that from the periodic table. And really the reason that we have to sort of convert everybody into moles is for really the third step and really the stoichiometry step of it, which is the mole to mole relationship. And remember that from any sort of equation that you got going on there, you could really use the coefficients, and really stoichiometry is nothing more than just using the coefficients as conversion factors. So we could say for every 2 moles of A, we get 3 moles of B. For every 2 moles of A we toss in there, we get 4 moles of C. For every 3 moles of B that we toss in there, we get 4 moles of C. So remember that these are all equalities, and again, they're equal to each other in terms of stoichiometry and sort of proportion that you need to toss in there for this reaction to take place. And that really is the whole goal of stoichiometry, is you really sort of have information about somebody in the reaction that you're not interested in, but you're interested in somebody else. Maybe you're interested in another reactant, maybe you're interested in another product, and you need a way to really go from one to the other. So again, instead of looking it up in a table, we use the actual equation really as sort of our place that we get our conversions from. And the last step is sometimes needed, sometimes not needed, but oftentimes it is needed. You should always be in moles at this point, and then you want to go to some other units. So very common in basic stoichiometry problems or stoichiometry problems in general. We use molar mass here on the back end of the calculation to go from moles back to grams, which is a very, very common way of doing it. We talked about, I think, very briefly there at the end as well, of the idea of limiting reagents. Thank you. And limiting reagents and really excess reagents would sort of go with them as well. They are also sometimes referred to as limiting reactants and excess reactants. When we do a reaction, not always, and in most cases, there's usually some reactant first. So there's some reagent that basically will get completely used up. And there's usually one where you have plenty of. So the limiting reagent is the one that gets used up first in the reaction. And the excess reagent is the one that you have left over when the reaction is done. So for example, the one you did yesterday or last week, you weighed out a certain amount of grams of the potassium iodide, and you took a bunch of I think it was lead 2 nitrate from the bottle, and you had way more of the liquid part, right, left over. You poured it in there. So in that case, the potassium iodide was your limiting reagent. The lead 2 nitrate was your excess reagent. The way that we calculate limiting reagent problems, which we will talk about here right now, is the good news is it's sort of the same 4 steps. The only additional step is somewhere along the way, you do need to do some type of calculation to figure out which one is the limiting reagent. So we'll get into that right now. Any questions though on this stuff that we talked about last time? So let's talk about that a little bit more. As I think we also talked about last time, the importance of a limiting reagent or reactant is it is always the one that determines pretty much how much product you can produce. So I think I did this simple sort of thing last time, where if we're taking A and B and we want to make A and B, And if A was our limiting reagent, once we pretty much use up all of the A, there will be no possibility at all to make any more product. So the amount of limiting reagent, always the one that determines how much product you make. And that is why when you do these type of calculations, you do need to take a moment there and do a calculation to figure out which one is your limiting reagent, because you want to use your limiting reagent to figure out how much product that you produce. And that again would be your theoretical yield, as we've been talking about, would be the maximum amount that you could produce in that reaction. So limiting reagents, again, get used up first in the reaction. How do you know if you really do have a sort of limiting reagent problem? You need to take that sort of extra step to determine the limiting reagent. And it's really based on the information that's given to you. So if you are given enough information about all the reactants that you basically could get 2 moles, that for sure is a limiting reagent problem. So if you're given information in a problem and you look at the information and it's basically about both reactants, or maybe all the reactants, and you're able to convert that information into moles without anything else defined, it definitely is a limiting reagent problem, and you need to take that extra step to determine which one's a limiting reagent. The ones that we did previous to this, if you look back, you pretty much was given one piece of information. Maybe you're given information about a reactant, maybe you're given information about a product, but you're just given one piece of information. And so when you're just given one piece of information, that's a basic stoichiometry problem that you follow the 4 steps. And if you're given one piece of information and that information is a reactant, it's assumed that that guy that they gave you is the limiting reagent. So that's why we kind of just jump right into the stoichiometry part when you're just given, say, information about one reactant. But definitely if you're given information about both reactants and you have a way to get both of that reactants into moles, you do need to take that additional step to figure out which one is the limiting reagent. That will also lead you to the excess reagent, as we talked about as well. It will allow you to, and a very common question is, how much of your excess reagent is left over at the end of the reaction? So that is a very common sort of process. So there are several different ways that you can solve limiting reagent problems. I'm going to show you obviously one way, but there are actually multiple ways that you could do it. But the way I'm going to show you is based off of sort of what we've been doing, and you really sort of follow the same steps. So first step again would be balance the equation. Second step would be convert to moles, and pretty much no matter what method you use, those are always the first 2 steps that you do. So the additional step that we'll do when we solve limiting reagent problems happens right around here. We're actually going to do a calculation to determine the limiting reagent. And then once we do that, we will then kind of pick up like normal. We'll go to mole relationship using the limiting reagent. And then we'll convert moles to some other unit if necessary. So this sort of method really does sort of follow the same one that we use for basic stoichiometry problems, where we just insert a very simple sort of stoichiometry calculation to allow us to figure out which one is the limiting reagent or not. So this is the method we'll use. Another method is to basically just do 2 separate stoichiometry problems, one from each reactant, and whichever one produces the least amount of product is both your limiting reagent and your theoretical yield. So there again, like I said, there's kind of multiple ways that you could kind of approach these problems. So if we were going to sort of put people together here, exercise buddies, we need a guy and a girl. And we could see in this case, we are obviously going to run out of guys first, which obviously means that that would be our limiting reagent in this example. We also can very simply here in this example see that we have 2 of our excess reagent left over, which would be the girls here. And again, those are very common sort of questions that are asked in this case. Clearly at this point, once we run out of the guys on the right there, no more buddies. Guy and girl buddies can be obviously made in this case. So let's take a look at this and sort of go through the steps of how we would approach a problem that involves, say, this reaction here. That was a limiting reagent type problem. So we'll use the numbers I think that are on there. Let me just scroll down to see what those were. All right. So 4 moles of sulfur and 20 moles of F2. Okay, so oops. So in this problem, we're going to basically assume that we're starting with 4 moles of sulfur and 20 moles of F2. So first off, we are obviously given both reactants in moles. And in this case, we definitely could get the moles in this case because they're given to us in moles. So right there tells us this is a limiting reagent problem. Again, we're able to get to the moles of the both reactants. Obviously, if we had grams, we would convert grams to moles in this case, and we're able to get there. So we'll follow the same steps as I laid out before. The first one obviously is our balanced equation, which clearly we have. Our second one, just like before, we'll convert to moles, which in this particular case, we actually don't need to do because it's again already in moles. Like a normal stoichiometry problem, if it was in grams, we would use the molar mass, convert it to moles, and we would be at that point. So because we do know it's a limiting reagent problem, we're now going to do the third step here, which is actually figure out which one is the limiting reactant. So we're going to figure out which one is the limiting reactant or reagent. And to do that, we're going to do just a very simple stoichiometry calculation between the two reactants. And what we're trying to figure out, for example, is I'm going to choose the sulfur in this case. And what I want to find out is if I want to use up all the sulfur that I'm starting with, how much F2 would I have to put in there? So if we think about these numbers up here, these are really our starting amounts, right, of what we're starting with in this reaction. So what I'm going to do now is do a calculation to basically figure out if I want to use up all the sulfur, how much F2 is needed. So this is basically what I'm trying to calculate here. This is going to tell me which one's the limiting reagent. So to do that, I'm going to start with my sulfur because I want to use it all up. I'm going to go to the equation, do the mole to mole relationship between the sulfur and the F2. And that basically is a 1-to-3 relationship. So 1 mole sulfur on the bottom. So it cancels. 3 moles of F2 up on top. The moles of sulfur cancel. Tells me that 12 moles of F2 is needed. So this is just a very simple, I'm going to figure out I want to use up one of my reactants, how much of the other one I need to toss in there. First off, any question on that part there? Now, the important part is that is how many moles of F2 that I need to use up all my sulfur. I then want to compare it to how many moles of F2 I am starting with, which would be right about here. Yeah. So I need 12 moles to use up all the sulfur. I am starting 20 moles. Do I have enough? I do have enough, right? 20 is bigger than 12. So because I have enough, what this calculation basically just told us was I have enough. And because I have enough, that means that the F2 here is my excess reagent because I have enough. And by default, that would mean that the sulfur in this reaction would be my limiting reagent. So this is like the additional step that you need to do to basically figure out which one is the limiting reagent. Any questions on that little calculation there? Now, does it matter which one you choose? It doesn't. So I'm going to show you the other sort of calculation you could have done. You don't have to do them both, but just to show you that it comes out to sort of the same. If you decided to choose the other reactant, and you wanted to know, for example, if I want to use up all the F2, how much S would be needed. We would do the same very simple calculation. In this case, we would start with the 20 moles of my F2. Once again, using the mole-to-mole relationship between F2 and S, which is a 1-to-3 relationship there. That would divide, and we would take 20 divided by 3. Gives me 6.67 moles of sulfur is needed. So when I compare now between the sulfur that would be needed and the moles of sulfur I started with 4 moles, 6 moles. Do I have enough sulfur? I don't. So if I chose this calculation instead, it would still tell me the same thing. In this case, I don't have enough, which tells me sulfur is the limiting and the F2 is the excess. So it doesn't matter which one you choose to do this calculation with. You could choose either one. You don't have to do both. You could choose either one, but both will tell you the same result of which one is your limiting reagent and which one is your excess reagent. Question on that there. So once again, like I said, in this particular case, if you chose this one, you do not have enough. And again, that would tell you that this is your limiting, just like our other calculation did. So somewhere along the way, you need to do some type of calculation to determine which one's the limiting reagent. A very common mistake that a lot of people make is this. They get to the moles part, like the starting moles, the 4 moles of sulfur, for example, the 20 moles of F2, and go, well, sulfur has less moles, so it's the limiting reagent. And that's not always going to be the case. It may be the case in a lot of calculations that you do, but based on the stoichiometry of the equation, it may not always be the one with the smallest number of moles. So you can't just look at your starting moles and go, that one's smaller, so that's the limiting. You have to do some type of calculation to figure it out. Any questions on that? All right, so the importance of this, as we talked about, is it's always the limiting reagent that determines how much product that we make. So now that I know that the sulfur is my limiting reagent, I want to make sure that I go back and actually use the starting amount of sulfur to figure out how much product I would produce. So to finish up this problem here, we would take our 4 moles of sulfur, which is our starting amount of our limiting reagent. And we will do a mole-to-mole relationship between the limiting reagent and the product, which in this case happens to be a 1-to-1 relationship. 1 mole of sulfur gives me 1 mole of SF6. The moles of sulfur will cancel, and we would produce, in this case, 4 moles of SF6. We didn't ask for it in this case, but if we wanted grams, we would use the molar mass, right, of SF6, and we could get how many grams that would be. This would be our theoretical yield in moles, and if we calculated it in grams, that would be our theoretical yield in grams if we use the molar mass, which would be, well, obviously 1 sulfur and 6 or 6 of this. I wrote wrong number there. 6 of the fluorines. Any questions on that? So same basics kind of steps: balance equation, convert to moles, additional calculation to figure out limiting reagent, and then you pick up with the normal steps using the limiting reagent to figure out how much product that you would produce and convert to moles. Now, another very common sort of question that's asked of people when they do sort of limiting reagent problems is how much of the excess reagent is left over. So we could actually answer that using our calculation that we use to figure out which one is the limiting reagent. So we wanted to know how much of our excess is left over. We determined in this case that the F2 was our excess reagent, right? So our F2 was the excess reagent, and we started with 20 moles of it. And based on our calculation here, to figure out how much of the limiting, which one's the limiting reagent, we know that we need to use actually 12 moles of it to use up our limiting reagent, which means if we subtract our 12 moles, which is how much is needed. That would tell us that we have 8 moles of F2 left over, which obviously we could then figure out grams if we want to use the molar mass of how much is left over. So that is a very common sort of question that's asked, is how much is left over of your excess reagent. And you could use actually your calculation for your limiting reagent to help you do that. Now, mind you, I did kind of choose correctly here by doing that one, but if I happen to have used this calculation for my excess reagent, it would mean that I do need to go back and kind of do this calculation to figure out how much of the excess reagent I would need. So sometimes you choose luckily, and you can choose sort of the right one, and you don't have to kind of go back and do the calculation. But if your other guy was your excess, you would have to go back, obviously, and do it again. Any questions on that there? Like I said, this is one approach to limiting reagent problems. And as I said earlier, sort of the other very common approach is you would just do 2 separate calculations, one using sulfur to product and figure out how much grams you would produce, and one using the F2 to the product to how many grams. And again, whichever one would be the smallest number would be both your limiting reagent and your theoretical yield. Any questions on any of those steps there? All right, I tried one. Let's let you try one here. This is basically what we just went over here. All right, so why don't you try this one and see what you come up with. Using this reaction here, we want to know if we take 6.83 grams of iron and 9.34 grams of sulfur, how many grams of FeS would we produce? So we can give you some numbers here. Iron is 5585 and sulfur is 3207. All right, so take a couple of minutes, follow those steps that we talked about. Balance equation, convert to moles, find the limiting reagent, mole to mole relationship using the limiting reagent, and moles to some other unit. All right, so take a few and see what you come up with here. Yeah, so that's pretty much whatever they give you, you want to convert to moles. Yeah. So once again, obviously in this case, we do know it's a limiting reagent problem because we are starting with both grams of each reactant, which means we could definitely get. Okay, let's take a look, see how you're doing. So as I mentioned earlier, we are given the grams of both reactants. And that means definitely we could get to moles of both of them. So as I mentioned before, that is really your sort of key to know. Somewhere along the way, you need to figure out the limiting reagent part of it here. So the first couple of steps are really the same no matter what method there you choose. You're going to balance the equation, which it is. We do need to convert in this case what they gave us into moles. So using the periodic table and the molar mass, we will do that for our iron. We'll also do that for our sulfur, which is 3207 grams per mole. That is going to give us for our iron 6.83 divided by 5585, going to be 0.122 moles of iron. And for our sulfur, we're going to divide by 3207, going to give us 0.291 moles of sulfur. So once again, you could kind of think of these guys once again as sort of your starting amount of each of these. These are going to be the ones you're going to compare to, right, to see if you have enough. So now we get really to the part where we're going to figure out the limiting reagent. So once again here, you could choose either reactant and do that calculation to figure out how much of the other reactant you need to use it up. So in this case, I'm going to choose iron. So I want to know how much sulfur is needed to use up all the iron. So what that means is I'm going to take my starting amount of iron, which is 0.122 moles of iron. We're going to do a stoichiometry calculation between the two reactants, which in this case is a 1-to-1, makes it easy. 1 mole of iron is 1 mole of sulfur. The moles of iron cancel. 0.122 moles of sulfur is needed in this case. First off, any question on that calculation there? So now we want to really use the calculation to help us decide. So what we just figured out is if I want to use up all the iron, I would need to put in there 0.122 moles of sulfur. When I look at the amount of sulfur I am starting with, which is 0.291, do I have enough sulfur in this case? I do have enough, right? So I'm starting with 0.291 and I only need 0.122. That means because I have enough of the sulfur, in this case, the sulfur is our excess reagent. And by default, the other guy would be our limiting reagent, which would be the iron. Any questions on that there? Now that we made that really important determination, we're going to use the limiting reagent, which once again is the iron. And we want to make sure that we use the starting amount of it. So we'll use the starting amount of our limiting reagent, 0.122 moles of iron. Now we're going to do a mole-to-mole relationship between iron and the product here, which is what we're looking for, which also happens to be 1 mole of iron from the equation gives us 1 mole of iron 2 sulfide. The moles of iron cancel out. If I wanted the answer in moles, I could just be done, and that would be the answer, but I'm looking for grams, which means I need to convert my moles of iron 2 sulfide into grams using the molar mass. So that's not too bad. It's basically just adding those two numbers together. That is 5585 plus 3207 gets me 8792 grams per mole as the molar mass of our iron 2 sulfide. Using that in our last step here, 87.92 grams per mole of FeS. Moles cancel, and that gives us 0.122, which is about 10.7 grams of FeS. And since this is a product, this would be our theoretical yield based off of our starting amount in the reaction. Any questions on any of those steps? So really the same sort of basic 4 steps with that additional sort of calculation to figure out the limiting reagent. Any questions on any part of that, where any numbers came from? Now, it didn't ask in this particular case, but we could as well, if we want to know how much of our excess reagents left over, we could also do that calculation because we actually chose okay in this case. We know that we are starting with, in terms of moles, 0.291 moles of sulfur, which is our starting of our excess. We know from this calculation that we would need 0.122 moles of it to use it all up. And that would tell us that we would have 0.291 minus 0.122, 0.169 moles of sulfur, which if we want sort of a gram reference, molar mass of sulfur, 3207 from the periodic table. It's about 4.42 grams of sulfur is left over at the end of the reaction. We started with about 9.34 grams of sulfur in this reaction. We used about 3-ish or so grams, 3.5 grams or so of sulfur in this reaction. We have that much left over. How much of the limiting reagent should we have left over? Should be 0. Yeah, it should all get used up. So basically you should have 0 of that guy left over in this case, which would be the iron in this case, would basically have 0. Any questions on any of that there? Okay, let's try it. Here is here's what we just did. scroll across in case you want to look at it there. That's good. They got the same numbers. All right, why don't we try this one then? Based on which of the two is a limiting reagent and how many grams of our product will we be formed here? So this is the molar mass, so you don't have to calculate it for NH3. This is CO2, which would be 4401, and then this guy would be. So take a few minutes here, and again, follow the same steps, figure out the theoretical yield, and figure out obviously which one's the limiting reagent in this case. In this case, we have grams of the CO2, so that definitely is a way to get to moles for both of them. So definitely a limiting reagent problem because of that. We'll just follow our normal first steps, which is balance the equation, which it is. The next thing we need to do is convert to moles. So they were nice enough to give us the molar mass here. Once again, you would go to the periodic table if they did not do that for you and calculate it yourself. So 1703 for our NH3, 4401 for our CO2, and that is going to give us here 622.7 divided by 1703, about 36.56 moles of NH3, and 1241 divided by 4401, 2820, we'll call it 2820 moles of CO2 in this case. And once again, these are your starting amounts of each of these guys. At this point, because we recognize that it is a limiting reagent problem, we need to do that calculation. So once again, you could choose either reactant to with. So I'm going to figure out how much CO2 is needed. To use up all the NH3 we started with. So to do that, we will start with the moles of NH3. And we're basically just doing a little stoichiometry problem to figure out if I want to use up 100% of all those moles, how much of the CO2 I need to put in there. So from the equation, we can see it's a 2 mole to 1 mole relationship. So the 2 moles of NH3 would go on the bottom. The 1 mole of CO2 would go up on top. The moles would cancel there, giving us 3656 basically divided by 2, about 1828 moles of CO2 would be needed in this case, right? Any questions on that there? So we do want to compare. So once again, we're going to compare our calculation we just did, which is how many moles of CO2 to how many moles of CO2 we started with. And in this particular case, we do see we have enough. So we started with 28 moles of it, and we only need about 18 moles of it to do that. So we do have enough in this case. And that means that this would be our excess reagent. And by default, that would then mean our NH3 is our limiting reagent. So limiting reagent would be our NH3. Our CO2 here would be our excess. First off, any questions on that? This is also a good demonstration of what I was talking about earlier. The smaller number of moles here is actually the CO2, but it's actually the excess reagent. So you cannot just go based off of which one is the smaller number of moles. So you got to do the calculation to figure it out. So because of that, what we want to do is, again, go back to our limiting reagent and use the starting amount for that guy, which would be our 36.56 moles of NH3. We now can use our limiting reagent to figure out how much product. So between our limiting reagent and our product, it is a 2-to-1 relationship as well. So for every 2 moles of NH3, we get 1 mole of our product. And again, that's the stoichiometry from the balanced equation. And since we do want grams, we're going to use the molar mass that was provided for us to do that. And that would be 60.06 grams of our product per mole. Moles cancel, moles of NH3 cancel. So we're basically taking 3656 times 60.06 and dividing by 2, looks like. And it looks like it gets us something in the ballpark of 1098 grams of NH22CO. And again, since that is a product and based off of the equation, that would be our theoretical yield in this case. Any questions on that? Yeah. Do not to subtract for the water. No, so you would not subtract or do anything with the water. What you could do is, for example, if the question was how much of both products you would produce, what you would do is a second calculation. Once again, you would use the limiting reagent, and you would do the mole to mole relationship between the limiting reagent and water in this case. And that would give you 2 moles of NH3 to 1 mole of water, which then you can use the molar mass of water, which is 18.02 grams per mole from the periodic table. And if you did that calculation, you would end up with this number here, which is about 329.4 grams of water would be produced, and that would also be the theoretical yield of water. So there's 2 separate products, and they have sort of stoichiometry that you could actually produce in this case. Does that answer your question? Or it is. So we would produce, as a result of this, what I just did on the second calculation, that would be how much you would produce of water. Yeah. So that would also be, again, the theoretical yield of water. So you can do the theoretical yield for both products, and that's be how much you would produce. But yeah, some of, for example, the NH3 and some of the CO2 is going to end up in water. So some of the hydrogen from the NH3 and some of the oxygen from the CO2 will end up in the water part, while the other, everybody there looks like will end up in the other product. But in terms of how much you would get of each of them, they would both be based off of how much of the limiting reagent you would start with. So there could be questions, which is a good question. There could be questions where they will ask you, like, how much of both of the products you would produce. In the case here, like I just did, you would need to do 2 separate calculations, both from the limiting reagent to each of the products individually, to the products that you would produce. Now, in terms of conservation of mass, you would have the same molar mass of everybody on both sides, because the equation is balanced. So if you added up the molar mass of everybody on both sides, they're all the same elements. Those would be the exact same numbers. But in terms of how much you produce will be a little bit different based on the stoichiometry and what you start with in terms of grams. Other questions? Yeah. Both of them, yeah. So the bottom one would be, and obviously it wasn't asked originally in this question, but the bottom one would be if they asked, in addition to, how many grams of whatever that first guy was there, how many grams of water would you produce as well, which sometimes they may ask as well. So you could definitely do the same calculation to each of them, and that would be the theoretical yield of water. A lot of times, though, in a problem, a lot of times you are interested in maybe just one of the products, maybe like the precipitate or something like that you made. But you could potentially be asked about both of the products and stuff like that. So no matter what, if it is a problem that's a limiting reagent problem, you always have to use the limiting reagent problem to figure out any of the products, how much you would use. If it was a basic stoichiometry problem, like maybe we did earlier, where you were given just one of the reactants, you could assume that figure out how much product that you would produce. So that's really the difference between sort of a limiting reagent problem, like a basic stoichiometry problem. In a basic stoichiometry problem, there's an assumption that if you're just given one of the reactants, that's a limiting reagent already. So you don't have to do that step to figure it out. But definitely in the problems like these that we've been doing, that if you're given both reactants and the ability to get to moles, you have to figure it out for yourself, which one limiting reagent. And again, as you see in this example, which is a good one, It's not the smallest mole, so you do have to do that calculation to figure it out, not just go by the smallest number of moles. If you go by the smallest number of moles, you'll get lucky a lot of times, but it's not really the right way to do it. You do have a calculation to figure it out. Other questions on that? All right, so put that through there. It's good. It's got the same numbers, so it's good. All right. And again, we didn't do it here, but you could also go back and like we did before. I'll just leave it up there because you want to look at it later. And I'll go back and figure out the excess reagent left over as well through a similar calculation. In this particular case, we need to go back and sort of figure out, how much of that one we had. So let's talk a little bit about yields, which we've been sort of touching upon as we've been going through some of these calculations. And there's really three types of yields that we are oftentimes interested in. One is the theoretical yield, and the theoretical yield is pretty much what we've been calculating anytime from the equation and how much you start with. It's really your maximum yield that you should get. So when we do a calculation, we just did in the previous problem, we calculated the theoretical yield of both products. By the way, when you calculate a theoretical yield or an actual yield, a yield has to be a product. So it has to be on the right-hand side. You can't have a yield that's a reactant. So the yield is basically the product. So some type of product that has a B. If no side reactions happen, everything went perfect, that is maximally how much you should get out in that reaction. As you know, probably from your experiment last week, it's really hard to get all that yellow off of the beaker, right? And off of your glass stirring rod and wherever else it ended up in the experiment, perhaps. So along the way, when you actually do the experiment, there's a lot of places where maybe things don't go perfect and things get lost. Or maybe when you filtered your product last time, your solution that went through the filter paper was yellow, so that's like product you're losing as well. So there's a lot of places where things may not go well, and when you actually do the experiment, that is what is known as your actual yield. When you actually do the experiment, actually what you got. So for example, when you go back today, did you guys store it in your drawer for today? What? Oh, you put it in the oven. So your actual yield is after you put it in the oven, and obviously you took it out and you reweighed it. Actual yield of what you got there. And because we can see actual yield and divide it by the theoretical yield, and that will give us our percent yield. And typically on percent yield, we're looking for near 100. Larger number is good, but not too large, because if you get over 100%, that's usually not a good situation. So if you get over 100% yield, that usually means that your actual yield is too high. If you go over. And a very common way that could happen is like the experiment you did last week where you filtered it right and you had your solid on the paper and this thing was pretty wet, right? So if you didn't really put it in the oven long enough, or you didn't put it in your drawer and let it dry long enough, and you reweighed it wet still, or a little moist or a little damp, when you would weigh that, basically the mass that you would be getting is the solid you're interested in, but you also be getting some extra water weight, right? That you would count as your actual yield. And because you would count that as your actual yield, all that excess water weight, this number would be larger, which means you could get over 100%, which again is not such a great thing usually in most cases. So this is a case where 200% is not great. Yes. Usually, high 90s, mid 90s, it's really good, as you do it, as you go through it there. Now, actual yield, the good news is in book problems, it's typically given to you. So somewhere in the problem, they'll say, hey, this is actually what you produced. Obviously, in a laboratory situation, you would find it yourself. But in book problems, they're usually given to you. So theoretical yield is typically the one you need to find, and you need to find it either through a regular stoichiometry problem or like a limiting reagent type problem, one of those ways that you need to do it. So I think we'll skip this one. We'll do one more here. We'll do the next one. Two big numbers here, I think, for this one. Let's do this one, I think. Yeah, let's roll with this one here. Basically the same reaction in everybody as last time. We want to determine the percent yield if we started with 100 grams of each of our reactants and we produced 120 grams. That means we should have the same numbers as previously. So NH3 was 1703 grams per mole. CO2 was 4401, and our product there was 6006, I believe. All right, so we're looking for how many grams of, we're actually looking for the percent yield here. Okay, let's take a look here. So we're looking for the percent yield in this case, which means we need actual and theoretical. They again gave us the actual, which was 120. So we do need to find the theoretical, and again, that's going to come through a stoichiometry calculation. Once again, we are given the starting amounts of both of these guys, so we do know it's a limiting reagent sort of stoichiometry problem. So we'll start our normal step here. We still have our balanced equation. Using our molar mass here, we're going to convert into moles. And in this case, that gets us 100 divided by 1703. Going to give us a 5.872 moles of NH3, and 100 divided by 4401 gets us 2.272 moles of CO2. Once again, this would be our starting amount. At this point, we need to do our calculation to figure out which one's the limiting reagent. And as we've talked about, it really doesn't matter which one you choose. So I'm just going to choose this guy since it's up front. So we want to know how much CO2 is needed to use up all the NH3 here. So that is what I'm going to calculate. So starting with my NH3, which I want to use up completely. And to do that, using the stoichiometry between the two reactants, once again, it is a 2-to-1 relationship here. So 2 moles of NH3 on the bottom, 1 mole of CO2 up on top. So 5.872 divided by 2 gives me 2.936 moles of CO2 is needed in this case to do that. Once again, making our correct comparison, this is how much we need of CO2. This is how much we started of CO2. Do we have enough in this case? In this case, we do not have enough. We need 2.9, but we only have 2.2 to start with. That means that we do not have enough. And that also means that this CO2 is our limiting reagent. And in this case, our NH3 would be our excess reagent. Any questions on that determination? Once we determine that, once again, it is the limiting reagent. That is what we want to use to calculate our product. We also want to make sure that we go back to the starting amount of the limiting reagent, not what we used here or got here. We want the starting amount here to use in this calculation. So that is 2.272 moles of CO2, which is our starting amount. And doing our stoichiometry between CO2 and our product is a 1-to-1 relationship. So 1 mole of CO2 gives us 1 mole of our product. And since our actual yield is in grams, we do want to convert this to grams, so they're all in the same units. So using the molar mass that was given to us of 6006 grams per mole, NH2,2CO, that's going to give us basically 2.272 times 6006 gives us a 136.5 grams of our product here, which would be our theoretical yield. And that would obviously be the bottom part of what we need. Any questions on that calculation there? Now to finish it up here, we can calculate our percent yield by taking our actual divided by our theoretical and times them by 100. that would be our actual, which was 120 grams divided by 136.5, which is our theoretical, times 100, will give us a percent yield of about 87.91. Not terrible. Percent yield in this case. First off, any questions on that calculation? By the way, I think I might have mentioned it last time, but in case I didn't, when you are calculating percent yield, the units don't matter. You could do it in grams and grams. You could do it in moles and moles. As long as they're the same units on top and bottom for actual and theoretical, you could calculate the percent yield. So we commonly use grams, obviously, because that's a common unit that we use. So grams and grams is very common. But if you had moles and moles, you could also calculate the percent yield using them, as long as they're the same unit on top and bottom, so everything cancels out. You obviously can't do 1 grams and 1 moles because it won't come out correctly because they're not the same units. Any questions on percent yields, stoichiometry, limiting reagents, how to do any of that? Just before we finish here, just to go back to that question as well, just to let you know here about the water, I think we were asking about there. Where's that thing there? Okay, so although I did, when we were talking about calculating the amount of water here, I did kind of go back from the beginning and start calculating with the limiting reagent. You could have also, because we already had the moles of this guy from this calculation, you could have just did a mole to mole relationship between those two without going back to the beginning, and you'll get the same answer. So you don't necessarily use from the limiting reagent from the first guy. You then could do a simple relationship between the two, and it would give you the same answer. So you could do it either way in that case. Any questions on any of that stuff there? All right, that wraps up chapter 9 there. Couple